Welcome back to our discussion on rocks. So in part one of our discussion, we looked at igneous rocks and the classification of igneous rocks using texture and composition. We looked in part two, we looked at sedimentary rocks. We looked at the processes that form a sedimentary rock. We looked at the three classifications of sedimentary sediment, then took that sediment, lithified it into the three categories of sedimentary rocks: detrital, chemical, and organic type sedimentary rocks. So the last part of discussion, or part three, is now looking at metamorphic rocks. And so this first picture, if you were to compare the textural characteristics of the metamorphic rocks with respect to sedimentary and igneous rocks, one of the things that stand out in this picture is that you see, I'm going to use a non-geologic term here, swirls, or you see that the layers of minerals have been bent and folded and so forth. And this little pin in your right side of the screen, it just basically shows scale. So in this case, we have mafic mineral bands, I can use that term now, that have now been folded and bent and parallel to felsic type compositional mineral bands. So what is metamorphism? Metamorphism basically represents meta, meaning change, morphism, meaning form. And it basically is a transformation of pre-existing rock to a metamorphic rock through pressures and temperature relationships. So again, as the pre-existing rock is subjected to both pressure and temperature, the textural characteristics and compositional characteristics begin to change. What's important about the definition of metamorphism is the statement in the lower part of your slide that says all changes take place through what we call a solid state transformation. And this means that the flow or change and bending of minerals in which they align themselves in these various types of folds is again when the rock is still in a solid state. And when we say solid state, it's not in the solid state that we would look at when we pick up a typical rock, but I'm going to use a non-scientific word, and we're going to say when the rock is in a state of goo. So you can kind of envision the metamorphic changing through when pressures and temperatures are such that the rock is behaving more like hot taffy, but it really still is in a solid state. Because if it was to a point in which the solid state was put into a liquid state, then we would be back to magma, and we would be back to the igneous rock phases, which somewhat completes the rock cycle. So metamorphism represents a rock, pre-existing rock that is subjected to pressures and temperatures, and the changes, physical and chemical, are through a solid state transformation. So types of metamorphism, well, metamorphism probably begins temperature-wise to take place around 150 degrees centigrade with typical depths at about 5 kilometers below the Earth's surface. So given those conditions is when minerals begin to migrate and move around and change the physical and chemical characteristics of the pre-existing rock. So just about 5 kilometers below the Earth's surface, which I believe is probably just about 3 miles. So you have enough pressure at 3 miles below the Earth's surface to start making those changes. At those temperatures and pressures, compositionally anyway, new minerals have a tendency to form that indicates to the geologist that that rock, in fact, has been exposed to pressures and temperatures. So a couple minerals that I've just kind of pointed out in the lower part of your slide, quartz. And quartz is quartz. Quartz is regarded as a pretty tenacious mineral. If you notice, quartz has survived in igneous rocks, certainly survives in sedimentary rock environments, and survives in metamorphic rock environments. So quartz pretty tough to get rid of. Quartz can exist in all three states of types of rocks. However, chlorite, on the other hand, is a softer type mineral, and it typically forms only at a certain pressure and temperature relationship. So typically when a geologist is looking at the composition of a metamorphic rock and sees the presence of chlorite type minerals, that is a huge indication to the geologist that this rock has been subjected to pressures and temperatures. Muscovite also is another very important metamorphic type mineral, in which, again, if the rock has an abundant amount of muscovite, which is a phyllosilicate type mineral or a sheet type mineral, indicates, again, various pressures and temperatures that form that. So those are some what we refer to as index type minerals or types of minerals that would give rise to metamorphism. And there's others, and I just pointed out chlorite and muscovite. Two common types of metamorphism we'll look at in this class. There are actually several types of processes and conditions that allow rocks to be metamorphosed, but we'll look at the two most common type. One is known as contact metamorphism, and the second one is regional type metamorphism. In contact metamorphism, just what it sounds like, this is where hot magma comes in contact with solid rock. And so when we talk about plate tectonic processes later on, we're going to find that magma has a tendency, because of its density, to begin to rise and make its way up towards the lithosphere from the interior parts of the earth. And as it rises, it's very hot, it's 2,000 degrees, and it comes in contact with colder overlying rocks. And so you have to ask your question, where does the heat go from this 2,000 degree magma when it comes in contact with colder overlying rock? And we're going to use the word conduction. And conduction typically is a term that describes heat transfer through a solid. So as the magma comes in contact with the overlying colder rocks, the heat radiates from the magma through conduction, and as it permeates and moves through the colder rock, it now changes the surrounding rock, both physically and chemically, into a metamorphic type rock. And so if you look at the bottom of the screen and we look at the conditions of contact metamorphism, we say that contact metamorphism is a high heat condition with low pressure condition, meaning that in most cases contact metamorphism takes place closer to the surface of the earth or closer to the lithosphere, so the pressure isn't as much. So high heat, low pressure, it's a very localized metamorphism, mean geographically it doesn't have a tendency to metamorphose large areas. I regard contact metamorphism as very fast acting, like touching a hot frying pan. So for example, if you were to grab a handle of an iron skillet, you would immediately release it because it's very fast acting. So high heat, low pressure, localized, and fast acting. And I bring these bullet points up because we're going to look at regional metamorphism, and then we're going to make a comparison to contact metamorphism, and you can kind of look at the differences. So this is a slide showing an example of contact metamorphism. And so here you can see where you have a hot magma plume, and this hot magma is coming in contact with colder rock. And as the magma cools, it radiates its heat through conduction. And as it radiates its heat through conduction, the heat begins to change the outer area of the colder rock. And so where you see my arrow would be considered the metamorphic zone or contact zone of the process of contact metamorphism. And certainly you can see where they put a little city up here, indicating that it's closer to the surface of the earth, meaning that it's low pressure, high heat. The photograph you see at the lower part of your slide, this is an actual field picture of an example of contact metamorphism. And what I'm thinking and seeing here, because I have not been out in the field for this particular photo, but what I'm seeing is it appears to be a lava flow, possibly, where my arrow is, that has flowed over some colder rock. And so we can still initiate contact metamorphism. The lava flow, again, is 2,000 degrees. You would expect that to be for hot liquid rock. And as it flows over the colder rock below where my arrow is, you can see the little zone right here in which, through conduction, the heat has been radiated through and metamorphosed this area. If you were to look at that with a hand lens in the field, you would see some physical and you would see chemical changes that have taken place on this little layer in this little contact metamorphic zone. So this is a really good indication showing you that the lava flow is a lot younger than the rocks below. And that would be indicated because in order for this to be metamorphosed, these rocks below being older had to be there first. And so that's what this is probably indicating. And this looks like, just from the photo, that this is a very mafic type lava flow, which is probably, if it's mafic with an aphanitic texture, it's what kind of igneous rock? Hopefully you've said, oh, it must be basalt, because basalt is an aphanitic texture with a mafic type composition. The next type of metamorphism is basically the opposite of contact metamorphism, and this is a regional type of metamorphism. And so this is where pre-existing rock is subjected to very intense stresses, and we use the term stresses describing pressure, and strains, which is a term used in structural geology for deformation. So you can kind of envision these rocks are subjected to high pressures with high areas of deformation. So the rocks are being bent and faulted. And this is typically caused from mountain building forces. And so when we get into plate tectonics, we'll talk about different kinds of plate boundary interactions where, for example, one continent is moving into another continent. So these are high pressure forces, typically also producing very high temperatures. So when we look at the characteristics of regional metamorphism, we see that it represents a high heat, high pressure type environment, which, if we look at contact, the previous slide, it's a very high heat, low pressure. Regional metamorphism is very widespread geographically, so it's typically observed and looked at in huge mountain belts, so big, wide geographical areas. And we learned in contact metamorphism that's very local. And then regional metamorphism basically is analogous to experiencing a very slow sunburn, which means that if you compare that to contact metamorphism, we said it's like touching a frying pan. So in regional metamorphism, the metamorphism change or transfer is very, very slow. And it takes a lot of time for the rocks to bend and be metamorphosed. So again, for test purposes, you should be able to contrast and characterize the differences between a type of pre-existing rock being subjected to regional metamorphism versus contact metamorphism. So this next slide or picture then shows an example of regional type metamorphism. And here in your upper left-hand part of the slide, you see a mountain building. This is a plate tectonic boundary where we have one continent colliding with another continent. And then we can see where there would be a lot of high pressure and temperatures. The picture below B represents a plate tectonic convergent boundary in which you have an ocean plate moving beneath a continental plate. And again, you can see right in this area, there's a lot of pressure and a lot of temperature, which would typically regionally metamorphose rocks. And then this example on your right-hand side just kind of shows you the island of Japan. And if one were to look at the pattern of rocks produced in Japan, you would find these widespread mountain belts that have a pressure and temperature condition associated with the rocks, meaning that these rocks have been regionally metamorphosed. Okay, so let's now look at some metamorphic heat sources. We've just talked about contact with hot magma, so that's one heat source. Another heat source we need to consider is a heat source produced from what we call the geothermal gradient. And really what that represents is the deeper you go into the earth, temperatures increase. In fact, you may want to write this down. and that is the more depth or deeper into the earth, both pressure and temperature are going to increase. And this will be represented by the geothermal gradient. So when we look at the geothermal gradient, we can represent its characteristics by looking at a graph. And really what I always like to stress with my students over the semesters is if any one thing you can glean or learn from earth science is to learn how to interpret and read a graph. Because what do we know about a picture or a graph? It's worth 1,000 words. And so rather than memorize what's going on this graph, let's learn what this graph represents so that you don't have to memorize. And in other words, you can just look at a graph and be able to interpret that graph without having to memorize it. So in this graph, typically graphs are divided into an x-axis and a y-axis. And then really what the graph represents is the relationship between the y and the x-axis. So in this particular geothermal gradient temperature graph, it shows you that the y-axis is going to represent depth. So there's 1,000 kilometers below the Earth's surface, 2,000 kilometers below the Earth's surface, and then at the bottom of your screen, 3,000 kilometers. So you can see that where my arrow is represents the surface, and we're looking at a slice of the Earth in which it's getting deeper and deeper and deeper. The x-axis, where you see my arrow, represents the temperature. And if you look at the temperature, we can see that the temperature is increasing, 0, 1,000 degrees centigrade, 2,000, and so forth. So really what this geothermal gradient represents is a relationship between depth of the Earth and temperature of the Earth. And we already know that the deeper you move down to towards the interior parts of the Earth, the pressure and both temperature increases. So this black line then on your geothermal gradient graph indicates that relationship between temperature and depth. So let's kind of look at some scenarios. If temperature, for example, was uniform between depth and temperature, what type of line then would you expect to see in this graph that shows a universal change in temperature or a steady uniform change in temperature? You would expect the line to be straight down, like where we watch my arrow. It would be a straight down line. It would be a predictable amount of temperature given X amount of depth. But you don't see that kind of line in this geothermal gradient. So really what we would take from this right off the bat is the temperature is not uniform. Instead, what is basically happening to the Earth's temperature as we now we begin to increase the depth. So here we are at the surface where my arrow is. We begin now to go down. Let's go down to 1,000 kilometers. So here we start at 0 degrees. And by the time we get down to 1,000 kilometers, the temperature has already reached over 2,000 degrees. Okay, maybe we'll just interpolate here and say about 2,200 degrees. So I'm going to repeat that. We start going down in depth, watch my arrow, to 1,000 kilometers below the Earth's surface. I draw a straight line over this way, and my temperature then at 1,000 kilometers below is now 2,200. So in that little depth, in that little interval of 1,000 kilometers, what would you say about the temperature increase? Was it rapid or was it slow? Well, in this case, it was pretty rapid. So we could say that a gradient means a change. Okay, gradient means a change, and there was been a rapid gradient or a rapid change between 0 and 1,000 kilometers. In fact, it increased 2,000 degrees within the first 1,000 kilometers. Now, let's go ahead now and say, let's move down depth from 1,000 kilometers to 3,000 kilometers at the bottom of your screen. And temperature change, if we look at the 3,000 kilometer mark, basically it's just around 3,000 degrees by the time we hit 3,000 kilometers below the Earth's surface. So really, in about 2,000 more kilometers of depth, the temperature has only increased possibly 800 degrees centigrade. which means in this case, the gradient has slowed down. So the change, the amount of change has been very slow. So what we would interpret then in terms of the geothermal gradient is we would say that at the first 1,000 kilometers below the Earth's surface, we have a very steep, rapid change or a steep gradient. And then when we move from 1,000 kilometers to 3,000 kilometers, the gradient decreases and it slows down a little bit. So we would say then steep gradient at the upper part of the geothermal gradient and a less steep gradient as we enter into the depths. The real question is why? So there's a really good critical thinking question. Why is there such a steep gradient in the upper part of the lithosphere and asthenosphere, and yet the amount of heat is a less gradient in the interior parts of the Earth? Probably the short answer to that would be, think about this. When we live up in the lithosphere, would we consider the rocks being very cold rocks or very hot rocks? Well, fortunately, they're very cool and colder rocks, which is a good thing. But yet, when we already get into the interior parts of the Earth, it's already being brought up to temperature. It's already being heated. So really, what really happens is that the increase in temperature is very rapid because the rocks are cooler and colder up in the lithosphere. And then you can't put more heat into something that's already been heated when you get into the lower part of the mantle and interior parts of the Earth. And so where my arrow is already been up to heat. So again, you can't put heat into something that's already been heated. So therefore, the gradient or the change in that heat is a lot slower. So it's just really based on the fact that we have cooler rocks in the lithosphere. But what you should be able to do is exam time. You may see a picture of this geothermal gradient, and you should not memorize the geothermal gradient, but able to look at the picture and glean information based on this graph. Like, for example, if one says, what is the temperature of the Earth's interior at 1,500 kilometers depth? You should be able to find 1,500 kilometers depth, which is about right where my arrow is, and you should be able to draw a straight line over to the geothermal gradient curve. And then when that line intersects, go straight up, and you should be able to say, well, the temperature is probably somewhere around 27 or 2,800 degrees centigrade. Now, did you have to memorize that? And the answer is no. Instead, you learn how to pick off or glean information from the graph. And so I would advise any of your classes and any of the majors that you are taking out there to be able to look at some of these graphs, because again, a picture is worth 1,000 words. Let's move into pressure, and let's look at some relationships with respect to how pressure is associated with changing the textural and physical characteristics of the rock. And we've already learned with pressure that pressure increases with depth, and those various kinds of pressure will have a tendency to rearrange the minerals from a texture standpoint. Sometimes minerals can be compacted or elongated, and we'll look at some examples of that here in the next few slides. But let's look at two types of pressures. And the first type of pressure is going to be known as confining type pressures. And as you look at this block diagram under confining pressures, you see these arrows graphically drawn, and these arrows are exactly the same size. So this is a graphical representation of equal amounts of pressure being applied to all sides of this particular block. And we can even go as far as to say that this block is a piece of rock. And so we would say under confining pressures, we would say that the amount of pressure on all sides is uniform. It's all equal. And so when you drop down to the lower part of the slide, you see, for example, over here, you see where this particular rock has minerals. So these little circles indicate minerals. And under confining pressures, how would you characterize or describe the shape of the minerals? And really what's happening is the minerals are getting smaller, but they're all getting smaller uniformly. So for example, that mineral here is the same mineral here, it's just gotten smaller. So under confining pressures and uniform type stress, the term stress is the same word as pressure, um, the rock is squeezed uniformly, equally in all directions. So if you have confining pressures with uniform stresses, what would be the opposite? How about differential pressure? So this would be on the right side of the screen. And differential pressure means, in this case, the rock is being squeezed by different amounts of pressure. And so when you look at the block diagram below differential pressure, you see that each one of the arrows are graphically different in each one of their sizes. So you've got a larger arrow here, you've got a small arrow here, medium-sized arrow here, meaning that this particular block diagram is now being squeezed with different pressures. So the question then is, what happens to minerals that are in a rock and it's squeezed under differential pressure type of processes? And really what you find is, if you see the minerals down here in this block, and so these are aggregates of minerals in this particular rock that are very chaotically distributed, and under differential pressures, what happens to the minerals? Well, under differential pressures, the minerals now take on a specific type of orientation. In most cases, what we call a parallel type orientation. And that is a huge textural characteristic and feature that geologists look at with respect to categorizing the particular rock into the metamorphic class. So when we look at a texture and we see that the mineral grains are all aligning themselves and taking on a preferred orientation, that is a huge indication that this particular rock has been subjected to differential pressures. In fact, if you had to make a decision in which is more common on Earth, would it be confining pressures or would it be differential pressure? And the answer would more likely be that the Earth takes on more differential pressure. Very rarely would you see a situation in which, in a three-dimensional type rock, it's being uniformly stressed. And so really in the real world, differential pressures are probably much more common. So under differential pressures then, again, as we showed in the previous slide, we can take a rock of aggregate of minerals and subject it to metamorphism or differential pressures, and it will have a tendency to rearrange the mineral grains in some preferred direction. So again, if you look at image A on your left side, this is a rock that has not been metamorphosed. And in fact, let's say that this is a granite that has a very phaneritic texture. So think about what phaneritic means. And so we have these aggregate of minerals. It's a phaneritic texture, and we'll just throw in there, it's a felsic composition. This granite now has been subjected to regional metamorphism with high pressures and temperatures. And then you look at image B, and then how would you characterize the alignment of mineral grains in this case? Here you see now that the minerals are taking on a preferred parallel type orientation. And the term that geologists use to describe this preferred orientation, I like to use the word parallelism between minerals, is the word foliation. So when a rock then is foliated texturally, again, that tells the geologist that this particular rock has been subjected to pressures and temperatures. And, you know, there's graphs and there's illustrations that it tells the geologist exactly how much pressure and temperature a typical rock has sustained by just looking at the composition and how the grains are foliated and so forth. For this level of class, we just want to know that if there's a preferred orientation of grains, then this rock has undergone some type of pressure and temperature change. So here are some common foliated textural terms and names that are associated with metamorphic rocks. Probably one of the most common type metamorphic rocks is a metamorphic rock called gneiss. And what you see with gneiss is you see alternating light and dark bands. And you can certainly see these alternating felsic type compositions, alternating with mafic type compositions. You can certainly see that these minerals are taking on some preferred direction. And the question is, why do you think that when we look at a gneiss or a gneissic type metamorphic texture, that the mineral grains do in fact arrange themselves according to felsic type compositions and mafic compositions, light and dark colored bands? And the answer is probably more likely deals with density. So envision this rock in its gooiness state, if you will. And remember that metamorphic textures are produced in a solid state transformation. And so during its gooey state, the minerals are allowed to migrate and move. And so the light densities will follow each other. So mafic densities are a little bit more dense than felsic densities. So there's a tendency then for the mafic and felsic minerals to realign themselves. And so this picture down here is a very good picture of gneiss. And in fact, if you were out in the field and you saw an exposure that looked like this, you would be mesmerized and you would say, wow, what nice rocks. Sometimes when pressures and temperatures are a little bit less, so less than the gneiss type conditions, we get what I would refer to as a sub-parallel alignment of minerals. They're still very foliated, and compositionally there are different minerals in there like muscovite and so forth. And texturally, again, you get alignment of mineral grains, but it's not as pronounced and defined as the gneiss. And if you look at subparallel type foliation, this is known as a schistose texture. And the common metamorphic rock associated with a schistose type texture is a rock known as schist. And of course, you have to be very careful with this word because certainly if the C and S are missing, that really kind of changes the whole situation. So be very careful with schist. And again, if you look at this rock, this is some nice schist. And then the last rock to kind of conclude our part 3 of rocks, metamorphic, would be the next rock below in your slide. So look at the bottom right-hand side of your screen, and you may see this.